also. In a series LCR circuit connected across an AC source of variable frequency, obtain the expression for its impedance and draw a plot showing its variation with the frequency of the AC source. See the diagram here. See, this is the LCR circuit. Here the vector VL plus VC vector point at B, and at exactly perpendicular to this one, that is VR vector is there, and in between angle phi it is a V vector, that is a C point. Then if you are going to draw a closed circle, enclosed this one, then we will get here vector V is equal to Vm, then mod of Vr is equal to Vrm, then mod of Vl is equal to Vlm. Then from the figure the Pythagorean theorem gives, that is Vm square is equal to Vrm square plus Vlm minus Vcm whole square. Then if I am going to simplify this one, Vrm is equal to Im times R, and Vlm is equal to Im into XL. Then Vcm is equal to Im into XC. Substitute, that is Vm is equal to Im Z. Then after all these substitute, we will get Im Z whole square is equal to Imr whole square plus Im XL minus Im XC. Then Z square is equal to, then Z square is equal to R square plus XL minus XC whole square. Then therefore we can write Z is equal to under root of R square plus XL minus XC whole square. Then we can write this one as VC is greater than VL. Then if you are going to see the variation with frequency of the AC source diagram, it looks like this. Okay, here the impedance value, it is in the y-axis. Then here at this point Z is equal to R, and the frequency it is on the x-axis. Initially when the impedance value is decreases, when the frequency is increases. Then when Z is equal to R, then the impedance value is increases as the frequency will also increases. Then B part, what is the phase difference between the voltage across inductor and the capacitor at resonance in the LCR circuit? That is, the phase difference between the voltage across the inductor and the capacitor at resonance is 180 degree. At 180 degree resonance, it will be, the phase difference will be happened. Part C, when the inductor is connected to a 200 volt DC voltage, a current of 1 ampere flows through it. When the same inductor is connected to a 200 volts 50 Hz AC source, only 0.5 current flows. Explain why. Also calculate the self-inductance of the inductor. So this is because inductor will offer an additional impedance to AC due to its self-inductance. Then we can write R is equal to R is equal to VRM divided by IRMS, which is the value 200 divided by 1, which is nothing but 200 ohms. Then impedance of the inductor, that is Z is equal to VRMS divided by IRMS, which is equal to 200 divided by 0.5, which gives the result 400 ohms. Since Z is equal to under root of R square plus XL square, substitute the value, that is 400 square is equal to 400 square minus 200 square is equal to XL square. Then XL is equal to under root of 600 into 200, which give the values 346.4 ohms. Then inductance L is equal to XL divided by W, which gives the value 364.4 divided by 2 times 3.14 into 50, which gives the result 1.1 H. Our case, we have draw the diagram of a device which is used to decrease the high AC voltage into a low AC voltage and state its working principle. Write 4 sources of energy loss in this device. This is the diagram of the device. So here it is the primary coil is there, and here it is the secondary coil is there here. Okay. Then what happened, we will see here. When the alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux in the secondary and induces an EMF in it. It works on the mutual induction. Okay, it will work on the mutual induction principle. Then, sources of energy losses here. The first sources is the flux leakage between primary and secondary winding, and resistance of the windings. Then production of eddy current in the iron core and magnetization of the core. These are some of the energy losses in these devices. Part B, a small town with a demand of 1200 kilowatt of electric power at 220 volts is situated 20 km away from the electric plant, generating power at 440 volts. The resistance of the two-wire line carrying power is 0.5 amps per kilometer. The town gets the power from the line through a 4th transformer at a substation in the town. Estimate the line power loss in the form of heat. So here the total resistance of the line is equal to length X resistance per unit length, that is given by 40 kilometer into 0.5 ohms per kilometer, that is equal to 20 ohms. And the current flowing in the line 1, that is equal to P divided by V. Then I is equal to 1200 into 10 to the power of 3 divided by 4000. We get the value I current, that is equal to 300 amps. Then P is equal to I square into R. P is equal to I square into R. Therefore, line power loss in the form of heat is equal to, that is 300 square times 20, which gives the resultant 1800 kilowatt.